So this first notebook is about making sure that all the stuff that needs to be run can be run. It seems like, I don't know if all of them, but it seems like some Windows machines are not able to unpickle some of the objects. So a show of hands, who has gone through this page? Who's gone through this page successfully? Okay. So I will give a few more minutes for people to go through this page. I'll talk about what's in the setup and why some of this stuff is here before I get started with the main material. So as far as for it seems like with some of the Windows machines that have some pickled objects that don't seem to be readable back on Windows. Sorry about that. I was going to move away from pickling, but there were some objects that I couldn't save in a normal serialized format, so saved with pickling, risky move, it did not pay off. Good luck if you're on Windows. I'll try when I update this in the future to maybe test it out on a Windows machine and see if I can get a Windows compatible version. Yeah.
Is it a Windows issue or is it Python 2 versus Python 3? Because I had to adjust my page from Python 3 to read the code.
Oh, okay. So that may be an additional one because I'm using Python 2 when I pickled them, so I'm not surprised that.
Yes, Python 3 you need to slightly modify the loading. So the with statements you need to add read binary, and then you need to use the Latin 1 encoding.
Oh, okay. So someone said that it had to do, he thinks with maybe something like Python 3. So he changed it to read binary. I know that alone didn't work for some of you, but he also had it used with the Latin 1 encoding. So how did you add it? So down, let's see, here. So with the open. So what did you add here to make it work? So you did?
Yeah, so I added the read binary here, and then on the picker load, we add the encoding equals Latin 1.
So all this won't work on my.
Maybe this will.
This obviously won't work on my MacBook, so I'll run it here. But if you're a Windows user, you might want to add that to the with statements. So some of you who had the problems, let me know if it fixed it for you. Oh, it worked? Okay. Awesome. Thank you for finding a solution. So let me run through this. So mainly I'm going to be using pandas and a little bit of some visualization from Matplotlib and word cloud. In the end, we'll do some stuff with sklearn, but we're not going to go into in-depth, so I'm not expecting anyone to really know anything about sklearn. I am sort of expecting most people here have some familiarity with pandas. How many people here do? Okay, yay. How many people here know what a word cloud is? Okay, yeah, so it's basically image with some words where their sizes are associated with some weight. So we're going to be using that to explore our data set. Now I have some exercises in here. I also have an answers module. So if you've downloaded it, if you get to an exercise, it will throw an error until you've implemented it. If you don't want to do the exercise, I have a commented out import of the answer below it. So you can always just skip the exercises if you want. But it's not as fun. So if you've just installed NLTK depends on some data sets. So you can go and download them. I think there was an email sent out asking users to install some of these data sets. The easiest, smallest data set is the book collection. So we have the data set. I'll be talking about this data set. This is just, I put this notebook to try and find all the errors. Oh, this is one I modified. So just to see just to make sure I can find as many errors as early as possible. So we'll give 3 more minutes to see, to have people try and get as much stuff installed as possible. How How many people have run this notebook successfully now? Okay. Oh.
Somebody figured it out, tell me.
There's a link to the wheel file.
WHEEL?
The .whl.
Oh, okay.
You download that on the function.
So I think I should definitely make a branch of this project that's Windows compatible. That's what I'll probably, I'll work on doing that after this.
Where is specifier cannot implement check arrays?
Arrays. Which arrays is this again?
I think it's in SQL.
Ah. Oh, there you go, here. Oh, so maybe it's a version of sklearn, so try updating that. Because I know that.
This is the latest, right?
Yes. Because I know beforehand I was using, which one? And this one I was importing from an older module that scikit-learn had, and I would get a warning, so I updated scikit-learn. Okay, so I'm gonna go ahead and get started. If you're having any problems and you aren't able to run it, I did include static HTML versions of the run notebooks here. So you can still follow along even if it doesn't run. So let's start talking about what we're going to be doing today. So when you have a structured data set, what do you do to initially explore it? You maybe do value counts on the columns that contain categorical data. If it's numerical data, you might do like a mean. You can plot histograms and do all that kind of stuff. We know how to explore structured data. But how do we explore unstructured data? How do we explore text? So the idea is that we want to find out what's being said in the text. So that, of course, is a very nebulous statement, and that's sort of what this talk is looking to clear up. So what would be some initial ways you would think to explore text? Okay. Cool. I'm going to be working on this data set on job descriptions. So these are job descriptions from Indeed, and they were used in a HackerRank earlier this year. So how many people here have written a job description? Okay, cool. How many people have searched job descriptions and used that to make a job decision on which job to get? Okay, imagine, yeah. So let's see what we're going to do in this. So we're going through the introduction now. We're going to go over tokenization. We're going over TF.IDF. Don't worry, I'll actually explain what that is in case any of you don't know what it is. How many people here know what TF.IDF is? Okay, cool. How many people here have vaguely heard of it before? Okay. So we'll talk about visualizing using TF.IDF, and then we'll talk about some other NLP processes. So stemming and lemmatization to normalize the words, stop word removal. So this is a way of getting rid of less useful words, engrams, which is a way of us looking at sections of the text. And then in the end, we'll do some simple modeling just to explore how these features can affect our models. So one analogy I like to use with NLP is that it's like fishing. So you never want to go too deep or not deep enough, depending on what your problem is. So you want to figure out for your problem, what do you need to get out of the text? And then you need to figure out, how do I get to that exact depth? So in the case of what we're doing here, exploratory analysis, we don't need to go really super deep. We don't need to do syntax parsing or something like that, because we're just looking for a first pass understanding of what's in our data. On the other hand, if you're doing some much more complicated task with a problem that has to do with complicated statements made in the text, this cursory analysis wouldn't be sufficient enough. So with NLP, it's always first understand what you need to solve your problem, and then make sure that you don't overshoot or undershoot what you need. Oh, question? So let's see. So here's our data set. So the columns we have are an ID, which is just a generated ID for each job description, the description text, as well as some attributes of the job. So how many years experience is required? How much education is required? Is the job hourly? Is the job part-time? Is the job a supervisory position? So here we see that some of them, there's no experience required or no education needed. The other ones, so these are categorical variables. These are Boolean variables, or columns, I should say. So we have 4,300 jobs. So let's see. So one thing we could do, I'm going to give sort of a simple way of maybe explore text without having to do any NLP. Let's look at the character distributions, or the character lengths, I should say. So here we have an idea of how many characters are in our job descriptions. Does anyone here think this is a satisfactory exploration of the data? No. Okay, good. Okay, well, clearly the problem is that we have punctuation in there. So let's only look at alphanumeric. Okay, that didn't give us any more information. So clearly that's not going to work. We need to get at the meaning of what's in our data. So meaning in language, in text specifically, or also in spoken language, is from three pieces, depending on how you analyze it. People have made PhDs talking about this, so this is a simplification. So it's from the words. The words themselves have some meaning, but also the order they appear in creates new meaning. So it's not just words randomly put there. And also it's the context they're in. So we know from this some context for these words that we're going to find in the job descriptions. We know that there's job descriptions. This data set is from US jobs. We now have to consider how we're going to get the words and how we're going to get the context. So let's look at some example jobs, maybe get some inspiration. Okay, so here we see, let's see, Fleming Development Incorporated. They're talking about their company. They're talking about some benefits, so they promote with philosophy of promote with it from within. Basic job descriptions. So let's see. A lot of you mentioned tokenization as like the first thing to do when we're exploring the data. So, how many people here have implemented a tokenizer? Okay, cool. So Tokens, especially in the NLP context, I think probably more, this is a more general interpretation, it's referring to splitting text up into words. It can also be used in some contexts to split text into characters. For example, if you're talking about encryption, sometimes they'll refer to turning it into a stream of characters as tokenization. But here, obviously, we're talking about NLP, so we're only talking about splitting into words. But of course, there's a problem with this. What is a word? So, can anyone here give me just a definition of what they think a word is?
Sequence of characters.
A sequence of characters. So, in that case, so how would you split up a document into words then?
White spaces.
So white space, okay. So now we know that there are some characters which are not words, right? So in most, I'll say, English and similar language implementations, tokenization is about that. It's about identifying what a sequence of characters that we consider a word and not the characters that we don't consider a word. So we need to figure out what we want to actually, how do we actually want to define these things. So this is going to bring us to our first exercise. So again, we see our data. So here's some things we want to consider. How do you want to handle punctuation? If a word ends in a period, should the period be with the other characters in the last word, or should it be on its own? How should we treat contractions? English and a few other languages have these weird things where sometimes we'll just collapse words together. Should we split them up? What should happen to the apostrophe? Should we keep them together? How do you want to handle numbers? And how do you want to handle hyphens? So, as the first exercise, we have this example job description, which is, of course, very fake, but it just has lots of common situations that you run into with tokenization. So, some of the things to consider is, let's see, so we have job there, has the period at the end of it. Should that period be attached to job? The numbered list, should the token there be 1 and then another token for dot, or should it be a token 1 dot? And also, how do we want to handle salary? I mean, this is one of those things I was saying with NLP, depending on the context that you're dealing with, you might want to implement it differently. You can imagine if a salary appears in a job description, that might be an important thing to keep as a token. If, let's say, we're splitting up all punctuation as separate tokens, which is a common default implementation, then we'd have $50, comma, 3 zeros as tokens. And that's not going to be very useful. We have to then reconstruct salaries in a later process. So, I, of course, have already implemented my own tokenizer, so I'll talk about mine in a moment. But why don't you go ahead and implement a tokenizer? If you have any questions or anything else, I'll move on probably in a few minutes, and we'll see what you guys come up with.
Question.
Sure.
Data located?
There's, so when you checked out the project, there should have been a tar file, and when you unzipped it, and when you ran the setup file, it should have put it under a data folder.
Gotcha.
Okay, so there's like a first suggestion in case any of you you're not sure where to start. Generally, tokenization, at least in English and similar languages, is split up in between identifying the words or identifying the gaps. So sort of pick which one you want to identify. Do you want to write something that finds all the gaps and then just create a sequence of tokens for removing them. Or you want to find something that finds the words and then you just pull out all the words from the text. So just get an idea, how many people are still working on it? Okay. Is anyone finished?
I got on the space by space.
Okay, based on space, okay.
How do we split on multiple things?
So you might want to do something like a regex. So are you familiar with Python's regex module? Okay, cool. Well, this is why I'm using NLTK. So NLTK actually comes with a regex-based tokenizer that you can use. So I would say that might be a good one to start with. And I think that one has a setting about whether you're identifying gaps or not. So I'd say write like a good regex around that one might work.
You can be super lazy and just change what you want.
Oh, I'm sorry, what?
You can be super lazy and just change what you want.
Yes. So say as you're working on implementations, run it against a sample job description and see what's coming out, and see whether you like the output. Okay, how many people are still working? Okay, didn't see a lot of hands, so either they're very lost in thought or no one's working on it still. Okay. So I'm going to go and open up my answers. Hopefully it doesn't give away too much. Okay, excellent. So this is what I did to implement it. I know it's regexes are not exactly the most readable thing. So let me walk through about the decisions I made in making this. Okay, so first we know that we want to pull out the sequence of characters that define normal words, so like alphabetic characters, right? So we want to make sure that we get those guys. So this one's going to cover that. This is going to pull out a sequence of word-based characters. So the other thing I want is I want to be able to pull out the salaries. So I figured out what would be a good regex for identifying salaries. We have our currency symbols. We have some digits and commas and maybe dots, because in some area in Europe, for example, they use dots to separate out the thousands of digits. Every 3 digits. And then I want to pull the punctuation into something separate. So basically, if it's not a word character and it's not space, pull it into its own token. And I use the regex one for it. You could, almost as easily use just the Python RE module. So here, I'm not identifying the gaps, right? So I'm identifying the actual words. So if I were identifying the gaps, then it might be something like splitting on white space, which is something you see in some other very simplified tokenizers. Okay. So let's see the outputs. Okay, so we have, this is a description for a generic job, dot. Let's see how it did on our salary. Of course, I ran this beforehand, so I'm not actually going to be surprised. Oh, look, it worked. I totally wrote this in one try. It didn't take me a few tries or anything. Okay. So now, we're going to take it, we have a tokenized function now. And we're going to run that against our data frame. So we're just going to use the apply method against our job descriptions. And we're going to save it. So I also wrote a function for saving the functions that we create. If you want, you can look into the code at how that works. It's not really. I don't think it's not really important to this particular talk, but we'll probably need to use these functions later. So let's go on to TF.IDF. So we have the tokens now, but we need some sort of calculation to identifying what tokens are important. Because we're going to have lots of periods in there. We're going to have colons, and we're going to have the word the, as well as all this stuff about the particular job, like data scientist or hospital administrator. We're going to have these words in there as well, and we need to find some way of identifying which ones are important. So we're going to be using TF.IDF. So the loose description of TF.IDF is it's a number that will tell you how important a term is in a document relative to the corpus. To how important it is in the corpus. So really what that works is that you have your term frequency, which is the count of the number of times the term occurs in a document. Let's go in here. And then for IDF, I mean, strictly speaking, the intuitive understanding is that it's just 1 over the document frequency, but generally people use the log of 1 plus that value. It helps smooth out some of the things and gives some better, it works a little bit better than the very basic one, but this is, I would say, is sort of the default implementation you'll find of TF.IDF out there. So the thing is, we're not looking at TF.IDF by document, we're looking at TF.IDF across our corpus. So that means we need to look at an average TF.IDF. So here's some math. So let's go and actually look at it. So I've written a function here to calculate average TF.IDF. So the first thing we want to do is we want to turn it into bags. So you might have heard, who here has heard the term bag of words? Okay. Maybe also heard the term like document vector, but that I think is sometimes more general because there's other ways of generating that vector. But so the bag of words is basically a counter, like if you're familiar with the Python data structure, a counter of the words in a document or the terms. So we're going to take that. And we're just going to take our term rows. So we're going to pass something in here. We're just going to produce counts. And then we're going to sum up those counts. So we'll get the sum of the term frequency. And we'll get the document frequency from those as well by summing up just the keys. So we get just 1 per document. So this will give us, back from our calculation up here, so at this point, we will have the sum TF as well as this value for each of the terms. So now we have those. We can calculate the IDF. It's just taking the log of that value and using the number of term rows we have, or number of documents we have. So then we multiply that times the IDF, and we get the sum TF.IDF, and divide it by the number of documents to get the average TF.IDF. And now we'll have a data frame that has all the cool information we're looking for. So take my function, I'm going to give it the tokens we just generated before, and let's see what's there. Okay. Okay, this tells us some stuff, but not really much. We don't get really an idea of what's the meaning of these documents. We just know how these three values are distributed. So let's look at the actual words. So let's look. I'm going to sort by the sum TF. So this is going to be in ascending order. So what words do we expect to have low sum TF? Uncommon words, yeah. So these are words that occur very few times in the corpus. Teral, SDO has some abbreviations here. Okay, so what do we expect? What words do we expect to be at the other side of this? Yep. And remember, just the tokenization, so also comma and period are there. Because we haven't done any normalization yet. Okay, so what do we expect for low values of IDF? Also similar to, so we expect there to be sort of this contrary behavior between IDF and TF a little bit. So if it has a low IDF, then that means it occurs in many documents. So we'd expect similar words as that had very high TF. Yep. Okay, and low TF.IDF, or sorry, high TF.IDF. And what words do we expect here? Words that appear in maybe like one document. Teral again, some different ones. Well, what's interesting is now we know that these are words that occur in one document once. And so, at the very least, I get to teach you all a very fun, rare word. If you have a corpus and a word only, and a particular word only occurs once in that entire corpus, it's called a hapax legomenon. So there. Now I'll learned a new word today, or new phrase, I should say. Hapax legomenon. It's Greek, so I believe it means like a single word, or something like it basically means it means pretty much exactly what it is. It's a word that appears once, so it's a once word. I don't know. It's not like modern Greek. It's actually some older stuff like hapax. I don't really think is much of a used word anymore. Anyway, so the other side, average TF.IDF. For low values, yeah, we're expecting the same thing. But here's something interesting. So low values of TF.IDF, it's similar to high values of IDF. That's interesting. Why is that the lowest one? Okay, before we answer that, let's look at the other side. Interesting. High values of TF.IDF are all these stop words. This is not what we wanted at all. TF.IDF was supposed to solve all our problems, find the useful words for us. What's going wrong here?
Those are words.
Yeah, but we don't want these words. That's like and occurs in our corpus. That doesn't tell us anything. We want the cool, meaningful words. We don't want comma and asterisk. So what's wrong with how we've done it so far that we're seeing these words and not the cool words up here? Yeah, so basically TF.IDF doesn't solve all our problems for us. It's a vanilla implementation. There's honestly as many implementations as are people who have learned TF.IDF. There's many ways to do this, and really what we're seeing here, if we look at the sum TF and IDF, is the values of sum TF are way bigger. So it doesn't matter that the IDF is penalizing it. The sum TF is overriding it. So we could, of course, spend a long time tweaking to just the right weights to combine them, to find the right words, or as you were hinting at by saying that they're subwords, we could just remove the things, some of the things we don't like until we get some of the stuff we do. So, the way, now TF.IDF comes originally from the world of search, and the way it sort of works is that you have a query, and that query is made up of different terms. You break up that query into terms, you find their TF.IDF for all the documents, and then you sum that together and you get a score. There are, of course, many other implementations of search, but this is the sort of the basic implementation you might do in a course or something like that. So let's implement that. So first we need to make an index. So calculating TF.IDF for all our words, that would be expensive. And not only that, if you want to do it for every query, that'd be horrible. And why do you need to recalculate it again and again? Instead, what we can do is I'm going to build a corpus from words to documents so that I can initially pull out the documents that have any of the words I'm interested in and then do the calculation. So first we need to build a document index. So that's just taking out the tokens and doing the counter again. So just like we did before, and that's going to get our TF. So next we need to make what's called an inverted index. So the way that works is for each, I'm going to go over each one of the documents. And I'm going to go over each one of the words, and I'm going to update that in a dictionary. And that way we'll be able to go from our terms to the documents that contain them. So here we see all the IDs of the words that contain an exclamation mark. Okay. So let's import that tokenize that we saved earlier. Hopefully that works. Okay. Okay, so now our search. So the way that's going to work. So now we have, we're going to want the query. We're going to want our documents to be able to actually return stuff. We're going to want our normal index so that we can, once we get these IDs, look up our documents. We're going to want our inverted index and our IDF, because we don't want to, there's no reason to recalculate that. We want whatever processing is done. This is something that's important to consider in a lot of NLP things. If you're trying to do something that matches one piece of text to another, always make sure that the processing occurs on the same on both sides. I think probably everyone here says, oh, of course, that makes sense. But I would also advise you, always double check that the processing is the same on both sides. Because many situations, we think it's the same and then, oh, someone had a different version of something here, or they had a slightly different implementation here, or forgot to add a step here. So, and then we want to have the limit of the documents we return. So the way this is going to work is I'm going to process my query, and I'm going to get a set of the terms out. That way, if I look for something like job, it'll just search for job. No reason to multiply the score times for your query. That'd be an odd way of marking the importance of terms. So now we have these terms. We can get out the filter set, the set of IDs that contain any of our terms. So that's what we're doing here. So when we have that filter set, we can then get the TF for them, for the terms that are in our query. Now we have our IDF for the, for the term IDFs for our terms. So we multiply that. Now we have our TF.IDF. We do our score. We just sum them. And we sort. And let's see. So I'm going to search for data scientists in our jobs. Okay. Let's see what comes up first. Well, interesting. We got a DBA job. So Anyone have any reasons why we would get a DBA job instead of data scientist? Oh, I'm sorry, say what? Yeah, exactly, right? So this is something useful to consider. Remember I mentioned before about the order of words being important, right? So if you don't put something to look at the order, then if you have data in this thing and scientists somewhere else, well, it'll match that just the same as something talking about data scientists. So this is why language is the words, the order, the context. And other stuff, but we'll just stick to those three for now. Okay, so we have TF.IDF. So now we want to visualize it. Now, since a lot of you asked you questions about installing word cloud, I imagine it's already been spoiled how we're going to be visualizing this. But are there any other suggestions for how we might use TF.IDF to visualize what's in our corpus? Oh, histogram, yeah. So you could do like a plot for the different values they have there. Yes, so we're also going to be doing a scatter plot of TF versus IDF, just communicating similar information. Any other ideas?
Did you search for things that have periods or quotation marks?
Cool.
Instead of just data or whatever, would that also then register? Because you haven't claimed to take this out of your set yet, right?
Yes. Let's see. Oh, look. What Pennsylvania Family Service. I have no idea what this is, right? Because I didn't run this query. But it looks like it's just a long one. It's a really long one. And of course, yeah, exactly what you're hinting at happened, is that we searched for a common word and it just pulled up a really long document. Because you have long documents that are going to have lots of periods in them, or lots of the word and, or something like that. And of course, those are going to dominate. Which is why I said there's all sorts of different implementations of TF.IDF, and there are ones out there that are supposed to correct for document length. But the Wikipedia links have all that information. So let's go on to visualization. Okay. So we're gonna, those other attributes, we're gonna turn those into segments, because remember, we want to look at the context. So we have the generic context, so these are the job descriptions from the United States. But we want to look at more detailed context. So the jobs that require a lot of experience, the jobs that require a lot of education or very little education, jobs that are part-time or hourly. So I'm just going to build these filters that we're going to use later on, just pandas indexes. So really what's coming out of all these is a list of pandas series of Boolean values. Let's continue on. We're going to save these for future use. Average TF.IDF, we got that function we used from last time. Now, I also have those functions that I showed last time implemented another module. That's how I'm running them here. So let's see what's there. Okay, so these are the common words that we're expecting. Okay, so let's plot TF.IDF frequencies. Okay, that's a oh yeah, it's a function. Yeah, so let's run it. I guess this isn't quite frequency. This is just a scatter plot. I should have named it better. Okay, so this is a scatter plot. So let's talk about what's going on here. So we have some TF on the bottom, and we have IDF on the vertical axis. And I have the colors set to be connected to the average TF.IDF. So red means really high, blue means low. With absolute, with like dark red being the highest value, dark blue being the lowest value. So it's interesting that it seems like some TF is pretty much describing our TF.IDF values. With the exception of these guys, of course, they're going to be darker. This gets to the point that we talked about earlier about TF dominating, because we have these punctuation, these stop words, and all that stuff in there. So let's look at what these two guys are. So we want to find, first let's look at the ones that are over 20,000. So that's going to look at all these points. Okay, these are our stop words, right? These are the words with super high term frequency, also super high average TF.IDF because term frequency is dominating. Okay, so let's look at the ones right here that have greater than 2 IDF, but also greater than 10,000 TF. These two things. Asterisk and dot, even though I'm not sure, I don't think that's actually, that's a central dot, I believe. I don't think it's the period, and exactly, yeah. So this is what we're seeing from these, is that there's just lots of bulleted lists, and I'm sure if you've looked at job descriptions, you'll see those are common formats that people use. But obviously they're not so common that they're ubiquitous, otherwise they would have a lower IDF value. Okay, so now let's get to word clouds. So I find word clouds are a really fun and generally intuitive way of representing these weights for words. So let's see, let's do by average TF.IDF. Okay, so if I just presented this to you, could you really tell what this corpus was about? I mean, you'd be like, well, there's experience in there and I guess sales. You might be able to guess this job description, but it doesn't really give you a characterization. Almost any English data set is going to look not too different from this. Okay, let's try some of the other values. Let's do some TF. Okay, that definitely didn't work. IDF, if I presented this to you, you would think that this is clearly something about Microsoft Excel. I don't know what that is. And hanging is apparently very important. Maybe this has something to do with the 2000 election in Florida. I don't know, but we don't see Chad in here. I'm not surprised that's a really old reference, so I applaud you for those of you who laughed at it. You're very merciful. Okay. Okay. So I wrote this function that will, so that we don't have to go through each segment beforehand. What it will do is it will do the scatter plot, it'll do the overall word cloud, and then it will use those segments we made before, and it'll create a word cloud for each segment. So it takes a little bit while to run. So it's not too bad, it's only 11 plots it's going to do. Let's see. Okay, so we have 35,000 tokens. Here's our plot we saw above. And let's look through some of these categories. Okay, not really a lot of difference here or here. Yeah, basically all these less useful words are getting in our way. So, let's try and normalize some of these. So, how many people here have implemented stemming or lemmatization? How many people here know what lemmatization is? Okay. So for those who don't, so lemmatization is also sometimes called soft stemming, with the idea being that stemming, let's say in this word realize.
Get the root word.
Yeah, so stemming gets, well, it doesn't get you the root word, it gets you the stem. I'm sorry, I know that's pedantic, but they are technically different. Like, for example, if I had, one of the favorite words for talking about this issue is also a very long word, anti-disestablishmentarianism. Right, so if I were to stem that, I would get, any guesses? Establishment. Okay, so if I removed all the affixes, I would get that. But depending on what you actually are doing with your corpus, you want to configure what you remove. So yeah, if you want to remove all your affixes, you would get establishment. Because anything less than that is not technically derived from English, right? There is a connection between stable and establish, but the connection didn't occur in English, or didn't occur in modern English. So I would say that it's depending on the problems you face, sometimes you'll want to remove derivational suffixes. So that's like realize, hopeless. These are words that will take one word and create a related one, but it's oftentimes, it will turn like a noun to a verb or an adjective to a verb or to a noun, let's say. And then there's inflectional ones. Inflectional ones, it's the same word, it's just maybe a little bit of information has changed or it's a different function in the sentence. So oftentimes, you want to remove inflectional, because there's not a lot of meaning lost when you remove those, depending on what you're doing. If the number of things being referred to is important, don't remove inflectional stuff. Derivational stuff is, if you don't care as much for the very specific detail of the meaning of your words, then remove derivational, which is why you see a lot of simple search approaches remove derivational suffixes as well. Because you realize, real, requirement, you kind of want them to all be returned. You might do something where you have multiple indexes and you combine them somehow. Lemmatization, okay. So for those few people who know lemmatization, any volunteers to describe what it is?
Bring it down to its root word.
So again, it's not quite root word. So the definition of lemmatization has to do with a dictionary. So when you look up a word in a dictionary, let's say I look up calling. What will I see? I'll see present participle of the verb call. And it'll say like maybe what page, or if it's online, it'll be like a link to call. And that call will actually have the definition. So for these dictionary entries, I actually have the definition. That word up there, the head word, is traditionally called a lemma. So that's what lemmatization is. It's finding this canonical form. Now, again, the examples I'm giving here are English, and you can get very different considerations depending on the grammar of the language you're working on. English is pretty simple, but so with English, if you're looking for the stem of a word for, let's say, staging. No. Oh, darn it. Didn't get it quick enough. For the verbs to stage, the stem of that is stag. There we go. Now, what would the lemma be of the verb? Exactly, yeah. So you get to keep the meaningful form, the recognizable form, if you do lemmatization. The trade-offs, as we'll see here. So I included in the data set some lemmas I found from Lawrence Anthony's website. So you're going to need to hold in memory the mapping to do lemmatization. But with stemming, you need to run some algorithm to decide how you want to remove things. So it's oftentimes sort of this time-space trade-off. And of course, again, depending on the language, these trade-offs may look very different. So let's look. So here's some words. We have English lemmas. So if I wanted to find the lemma that had the most associated words, not surprisingly, it's B. B is a very weird word in English. It has all sorts of extra forms that other words don't have. So what's interesting here, remember what I said about make sure it has the same processing. This is already assuming a kind of tokenization. It's assuming that your tokenization splits off contractions at the apostrophe, keeping the apostrophe on the second part. So probably with this word, for this purpose, that's not really important, but it's just something to remember. Okay, so the next thing I want to look at, I want to find collisions. Well, which words, when I look them up, could there be multiple lemmas for? Because if there's too many of those, that might be a problem. Okay. So we have and would, that's the contractions have that issue. Okay, let's look at some non-contractions. Life and live. Well, plural of life is lives, and third person singular of live is lives, so that's where they collide. We see some other collisions here. It's not that bad. What, about 20 or so? Okay. Let's hope it doesn't actually affect us. I don't think it will. So now move on to our next exercise. So we now have this English lemmas. So this is a dictionary from a word in some form to its lemma. And I want you to implement a method on our same sample guy there that implements limmatization. I've already done stemming, or rather I should say Snowball. The Snowball project has already done stemming, and NLTK lets you use Snowball. So while you think about what you're going to do for limmatization, let me explain what Snowball is. There's this algorithm that's very common for stemming called a Porter stemmer. How many here have heard of that? Okay. So Porter stemmer is just sort of a very frequently used and well heard of algorithm for removing suffixes from English words. So the person behind that and a few other people made a special language for implementing stemmers called Snowball. And so you'll see in a lot of libraries like NLTK has it, OpenNLP, such as Java library for NLP, some search engines, they all have a lot of them have these Snowball stemmers already pre-built into them. So right now I'm just using the one from NLTK to do the stemming. I'm using the Snowball English stemmer, appropriately enough. So now I want everyone to implement limmatization. So your limmatization function should take the tokens, some tokens. So the tokens we output in the first exercise, this list of terms, and the mapping that we have available up above, this English lemmas. And it should output a new list of the lemmatized words. I would also say, let's consider the other stuff we want to do. We want to reduce case. We want to remove punctuation. So, So I expect this one might be a little bit easier than the first one just because, we already have the mapping provided. So, curiosity, how many people have finished? Okay. I will wait a little bit longer. Okay, how many people are still working on it? Oh, okay. We give, let's see, do 2 more minutes. So one thing I think some people implementing may want to consider, if you've never done a lematizer before, what do you want to happen if you don't find the lemma? So some of you may have noticed I actually ran a cell while you guys were working. It's just because the stemmer takes a little time, so I just ran it while you guys were working. Okay, is anyone else still working on this? Okay, so I think I'm just gonna move ahead and show what I did. It's not the most complicated function I've written, but yeah, it loops over them, throws away the non-alphanumeric ones, or non-alphabetic ones, I should say, lower cases them, and then looks up the lemma. If it's not there, uses what it was given. Okay, so as you can see here, the stemmer ran for about 30 seconds, which is why I ran it where you guys were working, because it can be very painful to sit here and stare at a crowd while I just wait for the processor to go. So let's see how long the lematizer will take. 1 second. What a wonderful thing if you have memory to use. Okay. So now let's do the analyze function. Excuse me. So first we're going to look at the stems, and then we'll look at the lemmas afterwards. So here we got our 11 plots. Okay. So now we have just under 16,000 stems. Let's look at this guy. Okay. So the bullets that we had before, they're gone. Okay, not surprising, we removed those. Okay, let's look at these words. Well, okay. It's a little bit better. We don't have the punctuation. We have what was manage or management, something related to experience. We have some more meaningful words. So you can get a rough idea of what was in the document, but as has already been pointed out, we have those common words, sometimes called stop words. Let's look at our different categories, or different segments, I should say. So 5+ years experience. Not a lot different. It looks like manage isn't as important for the 5+ years, at least I don't see it. Oh no, here it is, I just couldn't see it. Okay, no, it's important for both. Let's see, any good differences? It looks like sale is a little more important in 2 to 5 years than it is in 5+. Let's see. Work seems to be important for both of these, not a lot here. Okay, we're seeing clinic, interesting. Okay, so still can't really get a good idea of this. So let's look at lemmas. Although we have a larger amount of lemmas that are kept, I'm not really expecting much of difference in the effect here. Other than the word clouds might be a little bit easier to read. Okay, so overall, not much different than we saw with stemming. Although interesting, we do see, let's see, where's management doesn't appear to be as important, or manag, which is what was the stem version. Let's see. So does anyone see, okay, so we have manager here. We have management. Or we might have manage, and here we have manage. So stemming, as I said, is a little bit more aggressive. It will remove the derivational suffixes. So management is a derivation from manage, right? Manager is a derivation from manage. A lematizer doesn't necessarily remove that. You can, of course, always build a lemma dictionary that will do that for you, but in this case, this one's just, our lematizer is just removing inflectional suffixes. So see a little bit of a difference here.
What's the experience here is full word and over there is bad word?
Oh, let's see. So, experience is, oh. That's the overall, that's the first one. Okay, so, not much there, so let's save off our work, and we'll move on to the next section. So stop words, okay, so we identified this from almost the beginning. We're gonna need to remove these words. These words are blowing up our implementation of TF.IDF. And we don't want to spend the time having to find the perfect combination of TF.IDF to get rid of them. So we're just going to remove these because we know what they are, or do we? So I tried to find out the root of where the term stop words came from, and I couldn't seem to find it. It's such a weird, I don't know, for me, I find it's a very unintuitive way to refer to them. Does anyone here know the root of that? No? It's a mystery. Okay. Okay, so let's load our data back. So NLTK comes with its own set of stop words, and there's a lot of NLP and NLP related projects out there that come with a set of stop words. A common one that I see used by a lot of people is in Lucene, which is a Java-based search index. Even I think theirs is actually based off of someone else's, but I'm not sure about that. So I'm just going to be using the English one, but let's take a look at it. So we have a, about, above, after. Okay, so looking at these, anyone here care to take a guess what these things have in common, other than just their TF.IDF? Like, grammatically or their meaning-wise, semantically, what do these have in common? Very context-specific. How do you mean? Not very. Okay, so how do you mean?
Also, if the word is court, then it would be specific to a baseball court or a court of law. It's not limited application, whereas between the law and did,
Yeah, so basically the meaning they don't contain a lot of meaning in it. If I just say, by, can, couldn't, you don't really know what I'm talking about if you just have those words. Oh, yes.
They're alternative. You need a subject with them to have any meaning.
You need a subject with them. Let's see. Oh yeah, so they can serve as subject. Yeah. So, that's interesting. I think that the linguistics description for what these, getting towards what you're describing, is these are function words. So they don't actually carry a lot of semantic weight themselves. They just help words relate to the context and to other words. So in this case, like for example, most. Okay, we sort of have a generic idea of what most means, but it's sort of like because everyone here is to some degree familiar with programming, so it's sort of like a function towards what you were saying with a sort of with a subject. But you need to pass in something to make must mean something, or most mean something. Most what? Most of what? Same with my. So I know when I say this is my phone, then we all know what that means when I say it. But if you were to talk about like, oh, this is my computer, it's the same my, but it has different meaning. So these are words that serve as functions. They don't really have their own meaning. So those are easy candidates to remove as stop words. But there are some situations where you wouldn't want to remove them. Remember beforehand where I said we're not going to do syntax parsing? Well, if we were, we would definitely not want to remove these because these are important cues in understanding syntax. But I would also suggest that there are other stop words depending on the domain. So a problem I worked on in a past job was a clinical. So in clinical documents, you often don't care about the word patient. Patient occurs all over the place. That's a stop word in clinical text. So in job descriptions, what do you guys think would be additional stop words you can add? Well, I have an exercise for you to do this. So first let's explore some words, let's look at different candidates. Yeah, I think that I think this conference isn't really too heavy on buzzwords. I've definitely seen much heavier buzzword conferences, right? Maybe like if some conferences, big data might be a stop word for them, or deep learning could be a stop word. So let's see. Let's look at our lemmas. Let's look at the TF.IDF values. So let's look at the highest TF.IDF for lemmas. Okay, so we see some ones in here that we know are definitely stop words, right? We see and to and the. We see all these words that we know. So is it just the case that all the top ones are going to be stop words? Oh. Experience, is that a stop word? Yes? Are you sure? Yeah, so it's not necessarily a stop word, right? Because it could actually be meaningful on a job. We expect it to occur a lot, but it's not. Well, it may be a stop word depending on what you're doing. But if you're trying to identify how much experience is needed, it's definitely not a stop word. Let's look at some others. Customer, skill, service. Who knows? These are hard. Well, let's see. Skill. What do you think? Stop word? Not stop word. Stop word? Okay, yeah, I agree. Of course, it depends on what we're doing. If we're looking for a list of skills, this would not be a stop word, but we're not doing that. Okay, so let's describe. So this is a distribution of the average TF.IDF, IDF, and some TF for lemmas. Okay. So it looks like, so let's look at some of these values up here. So it looks like for average TF.IDF, 75% are below 0.01. And we are looking at these ones with like values above 1. So these are definitely sort of abnormal for the amount of, for their value of average TF.IDF. Okay, so let's look at the words that are not stop words. Let's look at what the distribution is. Okay, so we see, okay, so, oh no, this is for the ones that are stop words, yes. So we see the average is way higher. It's like 80 times higher than for the 75th percentile, sorry. For the mean, it's not that much, oh, well, it's pretty big. It's pretty big. So, looks like we have definitely differences. So it definitely seems like average TF.IDF is a good indicator, but I don't know if I would make a hard and fast rule. When you implement your extra stop words, feel free to do a hard and fast rule. But I would say that you might remove some words that are useful. So let's look at the ones that are not stop words. Let's see what they look like. So we have experience, works. These are the high average TF.IDF non-stop words, at least non according to NLTK. Business client must. Oh, interesting. Must. That should have been in there. And let's look at the description. Okay. This was 0.04 for the general vocabulary. I would say go ahead and pick your own stop words now. You could either make a list or maybe just like select a group from the data frame, however you want to do it. So the thing with this one is that it could be super easy or super difficult depending on how you choose to do it. I would say if you're manually creating your list, this is sort of a good lesson about NLP is that there's nothing better than your own brain at understanding language. It just so happens that you operate much slower than a computer because you can do all this really cool stuff. And you're also not really built for doing NLP, you're built for just understanding language and hunting gazelle. So whenever you have the opportunity to have an offline process where you can utilize your own evolved expertise in the matter, that's definitely going to help you. Okay, how many are still working on it? Okay. Give it a little bit more. Okay, so before I show my answer, because I just did a handcrafted list where I created a few, any interesting implementations there? Any people want to talk about their implementation?
I was trying to do one that uses the 75% cutoff, but it's not successful.
Oh, okay.
And pandas closed it.
Oh, okay. Did anyone try the manual approach where they just looked for words on their own? Oh, so did you find any good words that you want to share?
We just thought about going about it, so we had like apply, click with the salary, benefits, and company.
Oh, okay, cool. Yeah, those are good ones. I would say one of our segments is hourly, so an hourly paid job versus a salary job. So I say maybe salary wouldn't be good, but click. That was one that I definitely didn't think of. That's definitely a good one. Let's look what I got. So let's see. I got requirement because that's so common. I don't know. That one didn't seem. This one must is one. I'm sort of surprised it wasn't in the NLTK one. Let's see. Position, work, ability, company, job, look, and able. Look isn't technically a function word, but it's used in English in a very generic way. Able, and then all the URLs were replaced with www.example.com. So when I was first going through this, I saw this coming up, so I had those removed. And then may, which could be a month, but is also a function word. It's like, you may do this. And I figure, okay, if I lose people referring to a specific month, I'm not going to be too upset about that. So now we get to look at the cleaned version. So this should definitely look better. So we've addressed all of our issues we were talking about before. We've gotten rid of the punctuation. We've collapsed some of the words down. We've removed the stop words. So we still see the same distribution, even though it's not quite as sharp of a drop. We've gotten rid of some words that were on the far right there. So let's see. If I were to show this word cloud to you, you'd probably be able to guess this is something, probably something about jobs, because you see experience and skill and services sale. This, I think, gives a good basic understanding of what's in our job. Let's look at the other segments up. 5+ years experience. Let's compare that to 2 to 5. Okay, so experience is big in both. Sale is slightly bigger in 2 to 5. Let's see. Interesting. So management is definitely bigger in the 5+ years. Customer is bigger in 2 to 5 years. Let's look at 1 to 2 now. Okay, let's see. Experience is still important. Not surprising because this is a segment defined by experience. Patient, that's interesting. By the way, whenever I'm looking at these and saying that's interesting, don't worry, I'm coming to that later. So let's look at master's degree, compare that to bachelor's. Medical, okay, interesting. Let's see. Experience is still big for both of those. Let's see. Associate's degree. Sale is definitely very big here. Let's look at hourly. Okay, service, hour. Okay, that's a good one. It looks like salary is apparently not that important here. So I think you would have been fine removing salary. Probably wouldn't hurt much. Well, we'll see. No spoilers. So part-time. Time here, hour. Let's see, supervising. Okay, so I don't know. This is definitely better than the previous ones, but this doesn't really give us a solid understanding. So we need to do something more to look at this. Remember we talked about these 3 parts to getting out the meaning. So we've looked at the words, we've done our work with the words, gotten the good words out. We have the context, we have these segments, we know it's job descriptions. We now need to look at that order. So the thing is, we don't want to do syntax parsing, that is slow. So, I know some of you may remember the outline from the beginning, but any suggestions for how we might look at the order of the words and get the meaning out of those? Yes, yes. So let's save off our work. So yeah, we're going to construct n-grams. So actually, before I go on to that one, anyone here know what n-grams are? Enough to explain them. Go for it.
It's when you have n consecutive words in a document and you consider one entity.
Exactly. See, it's not that bad. Okay. There's of course more complicated versions of that. One called a skipgram, which is where you also look at words with other words in between, but we're not looking at those. If you look up n-grams on Wikipedia, you can find that information. So, now, unigrams, bigrams, and trigrams have special names for low number ones, and of course, as someone who's obviously very interested in language, I noticed that they're mixing Latin and Greek roots, which is an abomination. But you know what they say, when in Rome, it's all Greek to me. Pause for laughter. Okay, so let's see what comes out from this very well-known sentence. The quick brown fox jumped over the lazy dog. So unigrams are just the terms. Bigrams are the quick brown fox. Trigrams, the quick brown fox jumped. So we have this sliding window of length n that moves out of the document. So, let's load our data. So there's something here, before you read and spoil it for yourselves. What's a problem we might have if we just run an n-gram extraction over our tokens? I'm sorry.
Like it would be expensive.
Well, it could be. So if you're doing like a large, so if you're pulling out like 5 grams over a huge corpus, yeah, that can be expensive, especially if you're doing some of the stuff like we're doing, like IDF. You can have this huge dictionary that's having this pointer from all these different words. So yeah, it can be expensive. It can be time consuming depending on how you're doing it. Any other problems though? Okay, that's another one. How about, is there a problem in, and could we potentially violate the meanings of these words depending on how we implement it?
Yeah. Taking the real means function, right?
Okay, well, so that's one that we sort of already accepted, right? Because we had to get rid of those to do the work beforehand. There's another way. There we go. Crossing sentences. So, and in this case, let's look at the sentence I have at the beginning here. N-grams are fixed width sequence of words pulled from a text. Let's use the following blah, blah, blah. So if I'm pulling out bigrams, I would get, depending on how you treat hyphenization, n-grams are fixed, so on. Then I get, we've dropped these, so we get pull, text, and then text, use. probably, because we probably dropped these words. Text and use. That's not a bigram in the sentences here. That's violated the meaning of what we're doing. So that means before we do n-grams, we have to do sentence boundary detection. So during the beginning, where I use this fishing analogy, I say only go so deep and no deeper. This is a situation where we're probably going deeper than we may have initially thought. We need to actually run a model-based program to split into sentences. That seems like a little bit more NLP than makes sense for exploratory work. But this is, I think, one of the situations where you have to remember that the sentence boundary detection models will be different for each corpus. So if you're exploring it, go ahead and use a default one. It'll probably work fine. And this is probably as deep as we'd want to go. Because anything after this, we're really getting, into really maybe diving too deep into the water here. So I'm just going to use what comes with NLTK. NLTK comes with the punched tokenizer. So that means I'm going to need to redo all the processing I did again. So I'm loading up my functions. I'm going to define a new function here. And the way it's going to work, it's going to take the description, it's going to break it up into sentences, and then it's just going to run all the functions over them. So let me run this. So this will take a few moments. It won't take that bad because we're not doing stemming, right? That took a really long time. Oh, look, it finished already, so I don't need to stall. Load the segments back. Okay, so now I'm going to create a convenience function for myself. NLTK comes with a function for generating n-grams, but you need to give it n. But I don't want to have to make a long call to NLTK.ngrams, so on. So I'm just going to make this function, it's going to wrap it. I'll pass it an n, and it will give me a function back, and then I'll take that function and I'll run it over, over the data frame. Here we go. So we have our sentences that we created up here. So this is all the sentence tokens that we have. So let's see. So what's contained in the sentences is a list of the processed sentences. So each row has a list of strings. And from that, I'm going to output a list of strings made up of the n-grams. So let's do it with 2 first. Actually, let's take a look at these. Employer midstream service something. ICR staff accept resume. Okay, so that's sort of what we expected. So let's analyze it. So, as you can see, we actually we are going to see a much larger set of terms here. So let's go ahead. So we're going to see a 1,600% increase in our vocabulary size with this. So let's see. There we go. So again, we still see this distribution, but I'm not sure if you remembered, in the last one we ran, this number was 10,000. So we have a much bigger vocabulary, but that means the sum TF is much lower now. So let's look at what's here. So overall, these are our bigrams. Okay, so we're seeing year experience, full-time, part-time, customer service, communication skills, or communication skill. So I think if you were to look at this, it would be pretty easy to tell you're talking about jobs. You might think you're talking about resumes. They do have similar vocabulary, but you definitely think this is somehow job related. So I think we have a good characterization here. Let's look at our segments. 5+ years. Minimum year, okay. Year experience, we expect those. Those are probably minimum years experience, maybe, or minimum and then some number. UI engineer and engineer UI. Interesting. Say 2+ years. Okay, it looks kind of similar, but we see bachelor degree is more important. Let's see, communication skills important in both. Your experience, minimum year. Oh, interesting. Maybe that's from, because remember we dropped all non-alphabetic words. Maybe this is from minimum X years experience, which means perhaps my tokenization algorithm was incorrect. This one I actually didn't know going into it, and so I invite any of you who want to continue exploring this afterwards, go try different things on those functions. But 1 to 2 years experience, that's what we have. Okay, high school, this looks like more prominent here than what we saw in the past. Let's see, for master's degree. Oh look, master's degree. Bachelor's degree. Oh, silver bullet. Interesting. Okay, what do you expect to be an important word for associate degree? Remember, so we have master's degree, had this one. Bachelor's degree had this one. What do you expect for associate's degree? Associate's degree. So it looks like we have a pretty strong signal for these segments. Okay, hourly. Per hour. Okay, that's pretty good. Driver license is kind of prominent there. Interesting. That's telling us some other intuitive information. I'm definitely liking bigrams. It's giving us some good info. Part-time. Colorado Spring. Say it with me now. Interesting. You didn't say it with me. Okay. Okay, supervising. Policy, procedure. Okay, this one's not giving us a lot. Okay, so we have a silver bullet in engineer UI, UI engineer. So let's use our search function who made all the way back when. And we're going to search for silver bullet. Okay. And sure enough, there's a company called, let's see, Silver Bullet. And they've posted many jobs on this data set. Here's the thing you have to think with n-grams. We're getting more information from our data set. And how many here have had experience with machine learning? Oh, okay, good. So then you know what it means when you're getting more information from your data set. You're overfitting to your data set. And that's really what n-grams are letting us do. They're letting us really just get specific information and understand our data set. So let's continue to look at larger n-grams and see how that continues to affect us as we look deeper. Okay, so let's do trigrams. So we're going to see, again, a 61% increase over bigrams, so not huge. You have to consider that once you get to a certain size for your vocabulary, especially in a very formulaic corpora, you may not see a continued explosion in the number of terms because you may have a lot of documents containing very similar phrases. So let's see. Okay, so it's flattening out. This went from 1200 to 300 for the maximum value here. Okay, let's see. Overall TF.IDF. Interesting. Equal opportunity employer. So this is what I was mentioning beforehand with formulaic sentences. You see a lot of job descriptions will have stuff like this. So let's look at some other stuff. Okay, minimum sales experience for 2 to 5. Okay, so definitely there's something interesting going on here. 2 to 5 years here. This is not very good. This is verbal written communication skill. We're seeing these formulaic sentences being represented many times. Because let's say you have a formulaic sentence that's, let's say, 6 tokens long. Well, how many trigrams will that produce? Multiple. Equal opportunity employer is probably not indicative of a job that needs 2 to 5 years experience. It's just a common phrase. Okay, 1 to 2 years. 1 to 2 years experience. Okay, that's definitely seems more meaningful. Huh. What?
Can you do stop n-grams? So equal opportunity employer, like equal and opportunity might be okay words. You would stop them independently, but when you see it as a phrase, like, so can you do stop n-grams?
You totally could. I didn't, but yes, I would say that'd be worthwhile doing. Then you might get some use out of the trigrams. Thought I heard someone else. Okay. Okay, so this is interesting. Do we really think Pikeville Medical Center is important to all jobs with master's degrees? Probably not. This is probably, again, us getting too deep into our own data set. Bachelor's degree, okay. Qualification, bachelor degree. Okay, that's good to see. Associate's degree. Yeah, okay, for a lot of the segments, we're seeing diminishing returns at this point. For some of them, like hourly, and for the 1 to 2 years experience, we're seeing some useful stuff like here, pay per hour, hour per week, high school diploma. Those are good. Part-time. Colorado Spring. And supervising, again, not a lot of useful stuff here. So, okay. So we're seeing the formulaic phrases, high school diploma, some of these things are matching our intuition, that's good. But we got these weird ones, Colorado Spring, Colorado, and engineer, UI engineer, and UI engineer, UI. So let's figure out what that is. Any guesses?
Missing punctuation.
Maybe, but then, so these are lemmas. So what would have been there before processing? But
Engineer parentheses UI engineer.
so that would get us engineer, UI engineer. But then why do we also have UI engineer, UI? But so engineering. So if you did like engineering : UI engineer, that would get us engineer, UI engineer. But why would we have UI engineer, UI?
UI engineering.
And then they said it again.
UI engineer for. I mean, it's the removal of all of the crap.
Well, that can cause a lot of oddities. That's not what this is, though. So, look at the SEO. This is like the classic implementation of SEO. What are they exploiting here? What are they getting? Why would they do this? Yeah, but to which part of the score are they actually working on, right? Because remember we talked about TF.IDF. So what are they boosting by doing this? TF, exactly. So people knew this formulation. So they said, I want to hire TF.IDF because I know in TF.IDF, if I have a high enough TF, it doesn't matter the IDF, I can overcome it. So I'm just going to repeat that. It's classic SEO. Sorry, does everyone here know what SEO stands for? Search engine optimization. So it's when you want to make sure that like your website's found, there's all sorts of stuff you can do, and there's a bit of an arms race between people who make indexes and people who put stuff in indexes. You know, the person who makes the index, they want their own algorithm to determine what's important. They don't want the people adding in there to be able to manipulate the importance. But the other people, on the other hand, you want your website or your job to be found, so you want to do stuff to get yourself more noticed. So this is probably useful when you're making a data set, especially for search. If you find this and you're like, oh, I need to come up with a way to solve that, which I'm not doing here. So let's look at quadrigrams. So we're not going to see much of an increase. Yeah, so we're not going to see much of an increase here. Let's see. So we still have the formulaic phrases are going to be important. We're going to see more of this overfitting, these jobs around that were connected to clinical or Pikeville medical beforehand. Those are going to be popping up. There we go. Okay, this one definitely looks very different. Remember, we went from having like a top value when we had just the lemma, the clean lemmas of like 10,000. Now it's down to 160, which means nothing's occurring a lot. Yeah, there's nothing really prominent here. There's just a bunch of these sort of generic phrases. 2 to 5 years experience. Again, formulaic phrases. At this point, we've dived too deep. And now we're just finding anglerfish, or whatever would be appropriate in this analogy. Let's see, anything interesting here? Sail, sail, sail. So, let's see. See again, this looks like it's part of an address. Probably, this might be an address, I don't know. Because we see road here and boulevard here. Maybe like similar what happened with www.example.com. Maybe the addresses were removed and they put all those in there. So let's go see what that sail, sail, sail is. We can probably guess what it is. Yeah?
Why are there more quadrigrams than trigrams?
So, let's see. So, the idea is that when you're making these n-grams, there's more unique ways to make a quadrigram than a trigram, right? So, ignoring how language works for a second, if let's say we're just picking 4 elements from our vocabulary, obviously you have a much bigger chance of, much bigger population of length 4 than length 3. The reason why it's not much bigger is because, like I said, how language works is you can't necessarily pick any 4 words and just put them together. So that's why we're not seeing a big increase, but we are seeing an increase. If you have a big, really diverse corpus, you would expect to see a continued increase for a large amount of n-grams. We have a relatively small corpus. It's not very diverse. They're all sort of the same kind of document. Sail here. Okay, yep. Looks like they did similar SEO at the bottom. Okay, so let's save off our work. So, I think I may be running out of time, but this isn't very much to do. This is a matter of fact, I would sort of encourage you, if you want to just run all the cells. To just play with this on your own, especially if you did your own implementations. Because what I did is I saved off the results from my models that I built. So I'm using decision trees. Let's see. So here's our data. So I'm using the TF.IDF vectorizer from sklearn. sklearn is a library in Python for doing machine learning. How many people here are familiar with sklearn? Okay, good. So, you know the argument in TF.IDF vectorizer called analyzer? Basically what we've done so far is implement that. We've implemented all the steps. So we can now use these different functions and construct our own analyzers. And then see how they perform differently for the model. So we're going to try and do some predictions of decision trees. We're going to try and predict education level, experience, and then the 3 Booleans, is hourly, is part-time, is supervisor. So I'm using decision tree because you can because a decision tree is pretty easy to explore. Here's one I made for, which one is this? I think this is hourly. So apologize, probably the font's too small to read. The top one is per hour. So if per hour has a lower TF.IDF, then it's going to go left. But if it goes right, we go from having 3,900 versus 451, which is 3,900 non-hourly jobs, 451 hourly. And we go to having 15 non-hourly, 118 hourly. So it helps us whittle down the data set. That's how decision trees work. They make pure and pure subsets of the data. So I don't have more time to explain it, but I would recommend you look on Wikipedia, but also my colleague from Indeed, Joe McCarthy, some of you may have went to his talk this morning. He did this really cool notebook that goes through decision trees, so you can also look through that. So I have the pre-built results. If you want to explore with your own, remove them. They take a little bit to run, which is why I didn't want to do it live. Let's see. So I've loaded up my features that I've already saved. And now I've used some widgets. Oh, there in this. Get rid of the warning. sklearn versions. Okay, so how many people here are familiar with cross-validation scores? How about with like what's learning curves, right? Cool. So what this is showing how well our model is doing on different sizes of the data, on the data it hasn't seen and the data it has seen. So here we have tokens. So the idea is the higher values you put on max depth, the more the tree can absorb the data. The lower values, the less it gets fitted to the data. Minimum samples leaf, the lower you go, the easier it'll be for it to make a new rule. The higher you go, the harder it will be for it to make a new rule or new leaf. Anyway, so these are basically controlling other values for overfitting. So here are the different features. So let's go look, let's throw everything in it. We're gonna throw our clean lemmas, we're gonna throw our bigrams and our trigrams. Oh, look, we got a slight improvement in score, which is, is good. But let's look at something else, experience. Okay, it's much worse. But hey, we're doing the full one. I bet you the other ones are probably worse. Like tokens is definitely gonna be worse than this, right? Da, da, da. Why do you think this would have happened? Well, fortunately, I made a word cloud out of the feature importances. Let's see what important features are here. 5 and 3, all these numbers we got rid of. So definitely this is a point of these different techniques are good for different situations. When we wanted to look at what sort of vocabulary we had, yeah, get rid of the numbers, that's fine. You want to build a model for predicting experience? It's probably not a good idea. So here we just have some scores. So I encourage you to take this notebook, try your own implementations, your own, the models, and experiment with them. If you want to use something other than decision trees, I just put some code here to wrap up training the model, so feel free to just modify that a little. I know we don't have a lot of time left. Any questions? Not for this data set. I have looked at that in the past. I find that for smaller data sets that don't have like a natural clusters, you don't get really good results. But yeah, that's definitely would be a fun one to look at. Yes, go with you.
So why did you use lemmatization instead of semi?
So.
And the question is, when do we use lemmatization and when do we use a semi?
So I would say the real reason I used it is I'm a language nerd and I like that it gives me real words back. Okay, but the more useful response would be, I would say, if you have vocabulary that may be a little bit more rare, so let's say you have specialized vocabulary, like let's say in clinical, you may not be able to find the words to do the data to do lemmatization. So stemming might actually be more useful in that situation. I would say if, on the other hand, if you are expecting someone to read the output, lemmatization is probably going to be better. And then of course, when you look at other languages, like if you have a language that has a very complex grammar, so that stemming would be a very difficult algorithm, lemmatization might be an easy way to do. So if let's say you were doing, like with Russian, lemmatization might be easier to implement than stemming. Next.
Could you update your GitHub repo with the pickled data set that works with it? I think if you do pickling with binary,
I'll give it a try.
thank you.
Would it ever be appropriate to look outside of your corpus to find the document frequencies and IDFs? Like so right now you're just looking at all job descriptions. I don't know, you might get another sense of the English language by looking at.
Yeah. So actually, that's an interesting thing. What you might do if you want to, let's say you have a small corpus, and you want to characterize what might be special in that corpus as a whole, You could maybe have a pre-built model that you've done on, let's say, Wikipedia, and then you could just compare the the words that have the most difference between the two of them. That might be something you could do. Yeah. Any other questions?
Looks like it. Let's thank Alex for that session.